In this video, I want to take a look at chemical kinetics under the microscope to develop a molecular level or microscopic model of why reaction speeds behave the way they do. In particular, why reaction rate is related to concentration in a direct way and how reaction rate is influenced by temperature. So let's begin by looking at a microscopic simulation of reaction kinetics. So in this simulation, the reaction we're going to be observing is A, the yellow balls, reacting with BC, the purple and blue balls, to form AB and C. I've set up the free energies so that this reaction is basically only spontaneous in the forward direction so that we don't have to worry about equilibrium issues. And I'm going to start with a certain number of molecules in the container, and I want us to pay attention to the reaction rates as the reaction occurs. So let's start by varying the number of molecules within this constant volume container to look at the effective concentration on reaction rate. So let's start with 10 molecules of A and 10 molecules of BC. You can see the molecules bouncing around such that not much is happening. I'm going to increase the temperature to encourage this reaction to go so that the total average energy is large enough to get molecules over the barrier. So you can see that the reaction rate is fairly rapid. We've generated 5 molecules of products now, and it's continuing to progress almost to 6. There's a little bit of back reaction going on. If I raise this even higher, we should see essentially only products forming. And you can see that now we've pushed the reaction almost completely to the product side with a little bit of back reaction. What I want to do now is actually double the concentrations by doubling the numbers of molecules in this constant volume container from 10 to 20. Watch what happens to the reaction rate. The reaction is very rapid now. We're already to the halfway point. It took a matter of a few seconds, and that reaction is going to continue to go forward at a much faster rate. The reason for that, if you pay attention to what's going on in the container, is that there are many more collisions between molecules in a given amount of time. Just because there's less space for the molecules to occupy, they're going to collide with each other much more often. This shows us the influence of concentration on reaction kinetics. Namely, as concentration is higher, the reaction rate goes up. This is true for both first order and second order kinetic models, and it confirms our intuition on the molecular level that reaction kinetics kind of comes down to molecules colliding with each other. So in that simulation, I hope you notice two things. First of all, the reaction rate increases with the concentrations of reactants. This actually we've seen before in the context of the differential rate laws. The standard rate is equal to the rate constant times the concentration of the reactants, right? And so as long as the exponent on the reactants is greater than 0, this indicates that the standard rate increases as the concentration increases, and that's the typical case with the exception of zero-order kinetics. The second thing to notice is that the reaction rate increases with temperature. When we increased the temperature of the molecules, they started moving more rapidly, and the reaction rate was much greater. The relationship between reaction rate and concentration is captured by the differential rate law. What about the relationship between the reaction rate and temperature? We can actually build this into the rate constant, the dependence of the rate constant on temperature, and this was done back in the day by Arrhenius, the same Arrhenius who was the namesake of the acid-base theory. Arrhenius noted that for a chemical reaction to occur, colliding molecules had to have some additional energy. If you paid attention during the simulation, you noticed that not all collisions led to reactions. Only collisions with sufficient energy, the energy called activation energy, led to reaction. Activation energy is sometimes abbreviated E sub A or delta G double dagger, where the double dagger is meant to indicate activation. We think about what fraction of molecules have enough energy to engage in reactions. We can actually look back to the Boltzmann distribution if we're thinking of the reactants as ideal gases. The fraction of molecules with energy greater than EA is related to e to the negative E sub A divided by RT. That's the fraction right here. That's related to this chunk of the distribution out this way, the fraction with energy greater than the activation energy. Notice what happens to the fraction of molecules with energy greater than EA as the temperature increases. As the temperature increases, the Boltzmann distribution moves out to the right? So to give you an example of a higher temperature distribution, might be something like this. And now there's a much larger fraction of molecules with energy greater than the activation energy, with increasing T. Because of that, we have more productive collisions, more collisions that actually lead to reaction per unit time, and as a consequence, the rate increases. Arrhenius was one of the key proponents of this idea, and what he did was he essentially applied this idea to the rate constant, noticing that in practice, in fact, the rate constant depends on temperature in this way, e to the negative EA divided by RT. As the temperature increases, the argument of the exponential becomes less negative, and the rate constant goes up. One other nice thing about this equation, which is called the Arrhenius equation, is that it gives us a means to calculate the activation energy by simply measuring the rate constant for various values of temperature. R is simply the gas constant, and so EA is the only remaining unknown if we're measuring the rate constant as a function of temperature. There are two important conceptual ideas built into the Arrhenius equation. One is this idea that as the temperature increases, K increases. And on this plot, you're seeing that for each of these curves, the rate constant increases as the temperature goes up. I've drawn multiple curves here for different values of the activation energy. And the second conceptual point that the Arrhenius equation can teach us is that increasing the activation energy affects the steepness of this increase of K with temperature. On the left-hand side, we have low activation energy, and for a low activation energy, the rate constant increases rapidly with temperature. In essence, there's a low energy barrier to rapid reaction, so it doesn't take much of a temperature increase to get us to a relatively high rate constant. On the other side, where we have high activation energy, it takes a lot of temperature, it takes a lot of thermal energy to get us to a place where the rate constant is high. The rate increases slowly with temperature when the activation energy is high, and the rate increases quickly with temperature when the activation energy is low or the activation barrier is low. Both of these ideas are consistent with a theory of chemical kinetics suggested by the simulation called the collision theory. Collision theory says that molecular collisions are necessary for a chemical reaction to occur, and more collisions per unit time translates into a faster reaction rate. That said, for a reaction to occur when two molecules collide, the molecules must have sufficient energy to collide, and that's related to the enthalpy of activation, which is a piece of activation energy. And they must collide with proper orientation, which is the other piece of activation free energy, delta S double dagger, or the entropy of activation. Furthermore, if we think of the molecules as ideal gases, as we often do in physical chemistry, for example, the number of molecules with enough energy to engage in productive collisions is dictated by the Boltzmann distribution, and that's connected directly to the Arrhenius equation. Finally, we can increase the concentrations of reactants or the temperature to increase the number of productive collisions occurring per unit time and increase the reaction rate.